Okay, so you will get it here at the end. So this is the whole implementation, and then here at the end you will get the research paper in the references. So inside references, this is the research paper for the Torture sample. So everything is available on internet. So if I just right click it, you will get the research paper. So this is proceedings of the Royal Society of something, mathematical, physical and engineering. So you can visit the PDF here. Take it download. This, and these are like published, I think, a couple of decades back. I think 1 or 2 decades back it was published. So if we go in the details of this algorithm, for example, then let's consider the problem here, what it is trying to solve. Okay, so this was the first example of quantum algorithm that performs better than the best classical algorithm works on. Okay, so this is how the quantum algorithm research started. Okay, and again it was on theory. These gates were described by people, etc., etc. No practical quantum computer was available. At that time, if you see this paper, it will not have something like IBM PhD change not like that. But this, it will talk about all the mathematical concepts, etc. They talked about how it is better for a larger qubit system, etc. And they showed that we have better algorithmic time complexity as compared to the known classical algorithms. So that is how, so for research publication, this is the theme. If you come up with a mechanism to implement a circuit that will then be evolved into an algorithm, okay, because ultimately the circuit itself, you pass on some input, different range of inputs, and then you prove that this circuit which is acting now as an algorithm, which is quantum circuit for quantum algorithm, is performing better than the respective classical algorithms that were known at that time or that are known today. So that can be limited quantum speed or a known quantum advantage for that algorithmic technique which is discussed. So these are some of the algorithms I think a couple of decades back people published, and IBM, when it started exposing their cloud and their quantum hardware, all these things are already ported. So 3-4 years back, when IBM had their global symposiums, people came from the world who were expert in this community, played with the IBM hardware and software, and they implemented these things, and those conference proceedings are today's documentation available on GitHub and IBM page. When every year they do that, they have at least one global conference or symposium where they collect the next level research and then they mainstream it and they put it into their, this is how their whole community is increasing and their whole documentation is also increasing. The same principle is followed by with the open source culture in software. The same thing is followed by Google, Amazon, everybody is trying to bring in more and more people across the globe to use their cloud, to use their quantum computers, and so that multiple people will contribute to the research and some new innovations will come into picture and the field will advance. Because it is a completely research-driven field. And this is happening all over the globe. Xanadu, they open sourced their first photonic device, which was large scale, that is Xanadu Borealis. And then for 1 year it was free, and people experimented on that. They talked about multiple ways of implementing algorithms, and accordingly those papers were published, and then now they have put it on their own journal. This is how the things are moving. So now this problem to start with, so because this is a singular problem, we can understand the circuit very quickly. So this is how typically anyone should start in order to understand an implementation of a quantum algorithm as a circuit, quantum circuit. So what it states is that we are given a hidden Boolean function. So it's a Boolean function. So with some inputs and series of inputs, it has only 0 or 1 value. Okay. Because it is a function, only one variable is there in the output. So the range contains this one, whether xn is 0 or 1 again. So there can be different inputs 0, 1, 1, 0, 1, 0, 0, 0, 0, 1, whatever. And cubic input string. So eventually the output will be only 0 or 1. So this is a Boolean function. Given a series of Boolean inputs, there should be some Boolean output. So now consider the way we used to do it in digital electronics, some function, some circuit that is giving me an output either in the form of final result as a 0 or 1. So for example, something happens and then this is suitable for traffic signal problem, for example. For example, there must be a lot of combinations of AND and OR and or logical conditional things. They have to supply that if this is signal is green, they only make that signal green. Something of that sort can just be visualized. Some combination of Boolean functions will also be resulting into a complicated Boolean function. So for that problem, these guys have solved it using quantum algorithm. So this is a Boolean function. And the property of a given Boolean function is that it is guaranteed to either be balanced or constant. So which means that a constant function returns all zeros or all ones for an input. Now again, what this algorithm does is that it tells you whether it is balanced or not balanced. So which means balanced means it gives same inputs for all zeros for all ones. And so constant function returns all zeros or ones for any input. So the way we have constant 0 and constant 1 function, right? Whatever here, this is a Boolean function, right? These are Boolean functions, right? So constant 0 is for any input, it will always return 0. And for here, for any input, it will always return 1. That is a constant function. And if we have balanced function, then it will return exactly zeros. The same number of outputs as zeros and ones. So half of all inputs is ones and half, the other half is zeros. So our task is to determine whether a given function is balanced or constant. So again, this might sound very preliminary, but still from an algorithmic performance perspective, this is a better solution. So here,
balance function means
your identity or negation will be a balance function, because every time the half number of inputs you will get 0 and half number of inputs you will get 1.
That means I am having 1000 bits of inputs.
So 500 it will give you 0 output and
the function is defined like this: f(x0, x1, x2) gives 0 or 1. So that is called string of function.
That is the definition of the function. No?
So that means for a string of bits, we are having either 1, 0 or 1, 1.
No, either 0 or 1 directly.
That's right. So how many number of bits should be there in a string?
So that is very little. So
for example, so in this case we want to say that it could be 1000.
It could be only 1 also.
If it is 1000.
1000.
So out of that 0, it will give either 0 or 1. So one single 0 or single 1, I am asking that thing.
So if it is 1000.
According to the definition, it is saying that for a string of bits, I am getting either 0 or 1. Right, sir? Now we are asking whether it is balanced or constant one. For balanced, we are saying that it will give half of the bits as 0, half of the bits as 1.
Half of the input
bits, yeah, exactly. Input bits. So meaning is that depending upon the number of inputs, we will be getting that many number of either half of the bits as 0, half of the bits as 1. This is our balance definition. But here this DJ function problem defines that it will give either 0 or 1. So I'm confused here in between these two things.
No, no. So this is the definition of the function. Okay. Yeah.
So definition
This
says
is
that-
the definition of the function. And this is the problem statement.
Now the definition says that there are n number of bits,
Correct.
right? And out of that it gives either 0 or 1.
That is the function definition. Now, this function can have two types of behaviors that we are trying to evaluate. One is that it will be either a constant function
Or it is a
or
balance.
it is a balanced function. When it is a constant function, let's say it has only one input, 0. Okay, so you can only one bit is one variable, right? So x, which occupies
It's
only.
a string, sir. It's not variable. It's a string, right?
But that can have only single value as well, no?
So x1 is 1 bit, x2 is other bit, right? Like this. So we are having string
So,
of bits.
I try to do it from single bit, let's do it.
Okay.
Then we will move to 2 bits, then 3 bits.
Okay.
Okay, so if it is single bit, it can have two values, 0 input or 1 input. For 0 input and 1 input, you can then have output as 0 or 1. Okay, so there also, how many types of functions we know in a single bit? These are the 4 types of functions that we know today.
Correct.
Correct?
Correct.
So we are saying that these two are balanced and these two are constant. Correct? Now you change it to 2 bit, for example. We will move to 2 bit now. Right? So if it is 2 bit, then again the number of inputs will be 4, 0, 0, 0, 1, 1, 0 or 1, 1. Now let's move to this problem. Then if it is 2 inputs, then you will have 4 values that will be possible combinations. For each combination, the output will be either 0 or 1.
Not 0, 1.
We know output will be 0.
If it is 0, 0, it should
Now,
be 0,
we
0,
define
right?
that it is 0, 0 or 1, 1. Likewise. Okay. So you will define it somehow. How it will come to that time.
Only my question was, if there are n bits in a string, it's not only one single bit as an output, it could be multiple bits, right?
But that definition we will have to check.
Because sir, just now we have talked, we have just concluded, when I am having 2 input bits, 0, 0, suppose it is identity, so it will give as 0, 0. If it is 1, 1 input, then it will give 1, 1. If it is negation, then 0.
So you will define for more number of bits whether it is 0, 0, 0 or 1, 1, 1. That we are calling as 0 and 1. Because there will be more number of states between 0 and 1 and that. Somehow like that. But the analogy is whether your function is constant or balanced. So ये जो डॉयस जोशा का ओरेकल हमने कल देखा था, उसका ये n-bit extension. This is just an n-bit extension of a single bit Dodge problem. So in this PPT, in this PPT, this Dodge oracle, this thing is nothing but Dodge Joshua algorithm, which is telling you whether, okay, so you are adding an extra bit and then you are in this PPT. So, how the quantum advantage is proven in this problem? So, let's consider that for classical solution to solve this problem, okay, so the classical solution to solve this problem will have those many number of queries to be passed on to the function, okay, to determine whether it is balanced or constant. So, in the best case, 2 queries to the oracle can determine if the hidden Boolean function is balanced. So, for example, if we get both 0, 0 and 1, 0, 0, 0 equal to 1, then we know the function is balanced as we have obtained 2 different outputs for different input streams. In the worst case, we continue to see the same output for each input we try, and we will have to check exactly for 2 raised to n combinations So if you have n bits as input, so 2 is to n values you have to pass on to the function in order to find out whether it is balanced or constant. So the classical solution in best case into queries you can determine, worst case is 2 is to n minus 1 queries you will need. So approximately it is taking exponential time in the worst case scenario, the algorithmic time complexity in the classical domain to solve this problem. I hope it is clear. In quantum domain, you will not have to fire 2 is to n queries. That is the best advantage to solve. That's the reason why we are saying that we will pass on only once, and for all different combinations, it will inherently check in this implementation of the function. That is the beauty of the algorithm. And that is how they proved that if you have exponential time complexity as in the classical solution part, here we will get a linear time. So this is the circuit for the transversal problem, where there are n input bits. For each input bit, we are applying a Hadamard operator. Okay. Then there is another input bit where also we are putting specifically one value we are giving. Then we are applying a Hadamard operator. Then there is this Deutsch oracle function that we will be adding, which will make sure that all different combinations will be evaluated to check for whether it is balanced or constant. And then again, to get the data back, we will again apply Hadamard operator to the input bits, okay, and only once, and we will get the output.
So this Hadamard gate will be single bit and all n bits will be continued?
No, these are n Hadamard gates. Okay, so but pictorially notation for quantum circuit. So when you will see the and these are the mathematical steps to implement it. So for n qubits, this is the mathematics. To understand it, for 2 qubits, they must have given a solution here. The constant oracle and balanced oracle कैसे implement करेंगे? And the working example for 2 input bits is given here. And then creating the quantum oracle. So this is where you can check and try it yourself. So this is 1, 2, 3, 4. So different CNOT gates have been shown here. Then these are 3 CNOT gates created. Then a negation gate created. Then QSC implementation for those is presented here. Oracle is a way to implement quantum circuit as something like a black box function. इसको हम C programming में method बोलते हैं. I will pass on something and I don't worry that I have some function which does addition of 2 numbers. Okay, I just pass on the 2 numbers and get the output as the addition. I don't care how much is
black box is basically
Oracle. Oracle is nothing but a function, but internally it is nothing but a quantum circuit. So we will try to, what we can do, we can copy this code from here, okay, and then we can create a new, so everyone will have to restart their server here. Mine is also restarted. So for running things on IBM, we will have to restart because now this is de-establishing the connection, so it will take some time. The server interesting. So please also do this in parallel, because we will be copying the code from GitHub and then we will be creating a new notebook and then running it on that new notebook. Okay, so this was the notebook instance, error starting kernel. Okay, so now this will not work because एक बार फिर से restart किया है ना यहाँ पे. You go here, you create in launcher a new notebook. So in the launcher you can have a Python key, IPython kernel, and start getting started with Grover. So some half-cooked implementation of Grover algorithms may be already done here. If you need only Python, you can use Python key here, etc. On the console, we will use the notebook instance. यहाँ पे this is untitled one, but we will call this as we need to get started. What I have done, I have renamed this notebook as RAIT-ACM. Okay, so we are trying to implement that algorithm. So what I did is I go here, I copy this. GitHub, yesterday we discussed, so type keys textbook GitHub. You will get it from there. So inside that there is a notebooks folder, within which there is CH algorithms folder, and then you have the implementations of multiple algorithms. So basically what it is doing, we are importing NumPy from NC, and we are doing from QSKit, we are importing IBM Quantum, AER, that is frameworks. So earlier, now I think they have modified it, but there were 4 different frameworks 3-4 years back on IBM. AER, ऐसे now that is changed. So, but it is also still reflecting in their libraries. So when QSKit providers.ibm we are getting this busy. So basically it is for searching the existing data centers. कौन सा लिस्ट busy data center है वहाँ पे मेरा query जाएगा. वो हार्डवेयर इंस्टेंस मुझे अवेलेबल करने के लिए या सिमुलेटेड इंस्टेंस अवेलेबल. Then from QSKit import quantum circuit and transpile. Then from QSKit visualization, plotting histogram library and then here. Now I will go here. We are setting the length of n-bit input string. Just defining a variable. Then constant oracle. Now we need to create our constant oracle. So we have to program for it. So how it is done? So what are we doing especially is that this is for 3 input qubit streams we are doing it. So Q0, Q2, Q3 and then Q3 we are putting a negation gate here. So you see in the code, n is equal to e, constant oracle we are trying to create, quantum circuit n plus 1, that is for 4 input values. Output will be np.random integers we are taking here and putting it, passing on the two parameter to this function method. And if output is equal 1, constant oracle dot x of n and constant oracle drop. That's what we are doing here. Right. Then balanced oracle we are creating. Then some bit string 101 we are passing because it is 3 qubit input. The string length is 3. And then we are implementing it. Next we do our control NOT gates using each input qubit as a control and the output qubit as the target. So here then we have created three CNOT gates. I will walk you through the code as well. Let me start this one. So balanced oracle, we are creating a quantum circuit of n plus 1 which is now 4 qubits. In bit stream 101 is passed as an input, then we are using x gates, that is negation gates. Okay. And we are calling the balanced oracle dot x function balanced oracle dot barrier. So we are creating a barrier here. This line is called as barrier. So you have got the idea is started, right? So you create a new notebook. Once you create a new notebook, you go to the GitHub link. That IBM QSK textbook GitHub करके type करना. So this is the github.com QSK textbook blog main notebooks. Is there any way to you just copy this one? Just try typing this one. I just keep it like that so that you can copy. And inside the notebooks you will get CH algorithms folder. Inside that folder you will get any issues? For the code. And to execute it, you will have to do that with the plugin and then open a new notebook here and then copy that code and try it. You can actually you can do that here as well. Textbook, blog, main, notebooks, quantum notebooks. You have CH hyphen algorithms, and within that you create a new notebook. try copying it. And write it. पूरा इंसान के let me know if you are able to do this. Now we go to the next.
constant one, the output is not constant one.
So we only you are creating आगे जाओगे तो पूरा फंक्शन लिखा होगा Let me know if you have reached here up to this point. This is the final generalized circuit that they call it, right? Okay, so where you have created for the complete range of n qubits. We are creating a circuit composition for balanced collaterals, etc. And then we are drawing this for a 3-qubit input stream. And then we have created the final histogram. So for using the local simulator, what is meant by local simulator? So one aspect is to understand this circuit, which is for a 3-qubit input stream. We are trying to implement the transversal oracle, okay, Deutsch oracle, which will check whether an input is a 0, 0, 0 or 1, 1, 1. So here it is telling us for 1025 how many times we have run. Accordingly, it will 1024 times we have run. Mostly all 1024 times we are getting 111 as the in the histogram, which means that we are running those many times on a simulator backend. What is a simulator backend? So there are classical supercomputers in some data center of IBM that are used to simulate a smaller qubit quantum computer. Okay, for our education purposes and testing purposes. Okay. So this up to this point, it is we have developed algorithms, we are visualizing the circuit, and then at this point we are trying to execute it on the simulator pattern. Okay. So there are two types of environments. One is a simulator. Simulator is not an actual quantum computer. It will give you a simulation of a quantum computer, because we know that for 2 raised to n qubits we need to provide all those within 2 raised to n states, and there is some classical supercomputers simulating that. Up to some 10, 20, 30 qubits we can do that. Okay, so IBM and GK, they are big data centers, so they make classical supercomputers used for creating quantum hardware simulation, and they make you available this instead of, because for these experiments we just need to test our algorithm with some inputs. Now if we want to run our algorithm with actual quantum computing hardware, then there is a different code. Then we have to pass it through a transpiler again and all. I will show you that also. And this is the generalized circuit. We will also try to create that. So this code, DJ Oracle, is the final function. So if you want to really study, this is the function to be studied. ये पूरा code है that is about the generalized Gauss-Joseph. So this is that function which will give you. This is function definition here. And then we will be calling it. Let's also create a function that takes this Oracle gate and performs the Gauss-Joseph algorithm. So this is your algorithm, which is completely dependent on the Oracle function, which is just about that. So now this at this point, this is the algorithm, and then finally, so we wrote the code for quantum oracle. उसके बाद generalized quantum oracle function, then we wrote the code for algorithm that will use the quantum oracle function, and then this is the code. Okay, this is, let's use these functions to play around with this algorithm. So then we are now actually using it and creating the circuits, and we are drawing the circuit now. Sometimes वो एक सेल से दूसरे सेल को रेस्पॉन्स I got similar problems. So I copied the full code in a single cell and seeing the results of running this circuit on a transpiler battery. We are using a transpiler here. So this is different from running it on a simulator mode. So, excuse me. I wanted to show you the cube experiment creativeness. So this is a very important thing I wanted to show everyone. Experimenting with the real device. So what we showed earlier was based on simulators. Now we will try to execute this on a real quantum computing hardware situated somewhere in US or Europe, and our cloud, through this IBM cloud computing service, we will be requesting for that hardware. You will see a queue. There is a message that comes. ऐसे बहुत सारे लोग हैं ना कि जिनको क्वांटम कंप्यूटिंग चाहिए, and people are requesting it to be at their cloud. So I want to show you that. Let's see that. So what are we doing? IBM node account. Okay, so the credentials it is loading this provider. IBM dot get provider as hub is equal to IBM-Q. Then we are requesting a specific backend which is least busy. So they are least busy service को देख के router जैसे connect करके in which hardware is least busy, then which is near to my geography through IBM cloud, it is then passed on as a request. Okay, so this is what can do. And अभी हम लोग job run करेंगे. So run our circuit. So least busy backend हम उसने आइडेंटिफाई किया. ये my geography के बेसिस पे यहाँ पे आएगा. So can you see here? Here when we run it and put it on GitHub, at that time IBM to Manila करके कोई तो backend था. Somewhere maybe in the United States. This person who ran this thing at that time was the output IBM. Right now what I am running, what output I am getting, IBM Osaka. So now you can Google and check. IBM Osaka might be some name to that data center backend. It physically existed somewhere. So my code will be run on IBM Osaka, which is the least busy backend for me right now. So there are multiple thousands of people running quantum algorithms across the world on IBM quantum computing hardware. So this using the least busy service will be identified which one is the least busy packet for my geography, and based on availability and response time etc. Correctly nearest to me hai, they might have some algorithm for that. And now because this is the backend identified, the code that we wrote, it will try to execute it on this backend. So run our circuit on the least busy backend. So qlist.students.monitor import job monitor and transcribe DJ circuit etc. etc. So this is trying to run this. So we will try to run it here now. So this is just a job and job monitor. We have just created the job. We have not executed the job yet. Now it is executed. I cannot run it. Run is executing my job. Job status is queued. It is saying job is queued. Next step.
Sir, if any package device is not available, then what type of message we will get?
तो कभी-कभी मिलता है, कभी नहीं मिलता. ये अभी भी देखो आप यहाँ पे कुर्सी, यहाँ पे देखिए ऊपर. See here, it is still queued. My job, it is showing me that my job is queued. The moment it will execute successfully, it will show me this, something like this. Job status, job has successfully run. Please wait for some time. And then once that executes, then we will again visualize the results like this. we have executed the most basic fundamental algorithm that claimed quantum advantage as opposed to the known.
How will we come to know that it is valid one or?
हाँ वही यहाँ पे इसके ऊपर से करते हैं।
It is showing that for that particular
This one, this input it is giving this. So it is constant very इस केस में।
one probability is 0.619.
हाँ,
This is a constant.
constant है शायद इसी का। But again see in running one actual machine will not give you exact results. हाँ मतलब ambiguity आएगा उसमें। That is the difference between running it on a simulator and running it on actual quantum device because there are errors. Yes.
So what is the significance of this graph, sir? Suppose I am giving 0, 0, 0 and probability is coming 0.0020. 62% probability, 62% times I got 1111 as well. For all different input streams statistics. But हमने उतनी बार input पास ऑन नहीं, हमने सिर्फ एक ही bit string पास ऑन की, उसके सारे combinations उसमें one go में evaluate. That bit string जो which we have given is 3 bit.
हाँ अभी इस केस में 4 bit है.
Okay.
इस केस में यहाँ पे देखिए N4 है. N is 4, यहाँ पे N4 है. See now the status has changed. Let's see here please. See पहले था अभी 2-3 minutes back it was job was active. Now the status is saying job is actively running. This is a live example of running a quantum algorithm on a real quantum computing hardware, okay, situated somewhere on this data center, IBM Osaka. So IBM must have multiple instances of their superconducting qubit hardware. I don't know where they are, but it is exposing their IBM Osaka backend. So backend is this cloud front-end का वो backend है. इसमें it will take care of executing this code that we wrote for a 4 input string, and it is currently actively running. And we will see what is the output. Yes. हाँ
directly you go there and you choose your environment. So technically this is and then you run all whether Python or any generate the circuits there.
So there are various frameworks provided by IBM. तो अभी हम जो कर रहे हैं we are taking an IBM lab. This is IBM lab. Okay. This instance is of IBM Jupyter lab. Okay. So through our credentials only it is getting connected at the backend to our API token. And अगर कोई API token नहीं है, authentication और authorization multi-factor authenticate किया हुआ हमारा API token नहीं है, तो ये रन ही नहीं होगा. So we have, so I am my login has a credential to connect to IBM quantum computing device because there is an API token that I am getting. So ये backend में ये सब REST API के through implement किया होता है, cloud computing service.
So meaning is this, so what I have understood from this, that first we have to generate a quantum circuit. If we are having authenticated API, that's API, token, then we will be able to connect that hardware. We can run the same circuit over there and results in the observation.
Yes, results will be supplied back to you.
Supplied back to you in observation.
And then we use visualization libraries and code again to visualize inputs, कौन से input का क्या output है.
So again, so we have to write the code for that.
So these 4 lines are just executing my job. So whatever we are writing, that is getting executed in this loop. After the job is successfully run. Please see.
This will be the last portion of our code. Right?
So now the job is successfully run on a real quantum computing hardware made available by IBM QSP. Okay. So now because we have got the results stored यहाँ पे कोई तो I will show you in visualization you will get that. So the job is successfully run. Then now get the results of the computation. So results is equal to job dot result. This is where we are getting the results. Then answer is equal to results dot get counts and then plot in histogram by mentioning answer as a parameter. See, 2, 3, 3, 4. 2, 3, 4. Sorry. One catch up नहीं मारा actually है ना. So see here, after running this is given maximum. What does it mean? So ideally, how to interpret this? The most likely result is 1111.
Sir, one more question. So this typical circuit, like 4 H gates and X indication, what is the logic behind this? Why we have arrived at this particular circuit?
So that is how we devised our quantum oracle for 4 input streams, n input streams. So वो logic है. The logic behind that is ये oracle है जो सिंगल बिट के लिए हमने किया था, उसका फाइनल सर्किट दिखा था है. This is the final circuit. So the logic here will get in this quickly. Basically, what we are doing is there are 4 types of functions: identity, negation, constant 0 and constant 1. So there are 4 different ways in which we are testing. So आइडेंटिटी के लिए हमने एक सर्किट यहाँ पे बनाया, निगेशन के लिए बनाया. दिस इज फॉर आइडेंटिटी, दिस इज फॉर निगेशन. बाय स्टडीइंग द इनपुट वैल्यूज एंड व्हाट आउटपुट शुड आई गेट, then which circuit will give me that output for that input. Accordingly for identity, negation, one single. हाँ तो ये हम जो 4 के लिए किए वो this is same for one circuit. So then here constant 1 and constant 0. Then all these 4 cases they are combined in a single circuit. So now you have one function that is a black box function for single qubit, which is the Deutsch oracle, which is this one. So ये circuit जो है, how do we solve the quantum computer in one query? So this is how we have done. So back to your answer. So this is how for single qubit they created this circuit. So this is based on our earlier 4 cases that I showed you. Then if black box function is constant, the system will be in a state of 1-1 after measurement. And if the black box function is variable, then the system will be in a state of 0-1. Advantage: exponential speed of time. Yes. function we have
So this is the observation. What we can conclude here?
it is a constant.
Constant one.
Constant.
अगर ये 0 होता है यहाँ पे 0 0. So that means constant 0 type से is it right?
This we can conclude that maximum probability is maximum probability of outcomes. Because these many times we have done it. इसमें से 62% में ये outcome मिला, which means that the function is a constant. Constant one या constant वो नहीं पता constant function.
But we are speaking.
Constant और नहीं constant और constant zero ये दो वेरिएशन से constant function के सिमिलर क्यूबिटी होता है. हाँ multiple क्यूबिटी से constant function. सारे मेजरमेंट एड्स उस एक जगह पे लेके आ रहे हैं वो सिंबलिज्म है बट इट इज गिविंग यू आउटपुट ईच दिस इज आउटपुट की इतने सारे एड्स के लिए आउटपुट प्रोबेबिलिटी इसलिए क्योंकि तुम्हें टाइम एक बार नहीं एग्जीक्यूट किया So, for 21 times.
This particular pattern is particular puzzle is not zero.
ये zero नहीं है. This particular first.
बैलेंस है और एक मीनिंग है
Is it like that?
हाँ उसका डेफिनेशन
Balance means this could be either balanced or it's not out
but balance
that balance is a
function definition function के boolean function
so if it is balanced with 0, if it is constant with 1, that's it.
ऐसा नहीं है मैथमेटिकल डेफिनेशन ऑफ फंक्शन है because it is a boolean function
I
आप
was
स्टैंडर्ड
thinking
को
that
जीरो
output
बता
will be 0, output will be 1. I was thinking in that way. So that's why it was
so there can be n number of ways to be given that creation balance and n number of ways there is a constant function so उसको टेस्ट करना है क्लासिकल मेथड से हम population n varies करने पड़ेंगे
single variable is working.
तो मतलब एक्सपोनेंशियल टाइम
Means out of 3 guys, either 1 0 1 I will put and it will give me for even if it is a good combination I will take it.
क्लासिकल में करना है अपनी बाहर
Using what this is my hardness, 0 plus 1 output will be but in classical either 1 0 1 for example 1 0 1 output or combination taking output.
Okay, so in classically the exponential type of velocity has been फिर the first ये जो 20 साल पहले उन्होंने मैथमेटिकली इशू बनाया जिस वक्त हमारे पास क्वांटम कंप्यूटर्स आएंगे उस पे हम एक्सक्लूड करते हैं तो दूसरी 6-7 years back when IBM created it we can run it from here. do not know. Ideal control that. And calculate the total 1 by n. And that's it. I was saying that we had actually our algorithm twice. We had the first time we had it on the simulator. Simulator is nothing but a classical supercomputer which is giving me the aim of the quantum computing. Why? Because up to 2 to 30 states, there can be a classical supercomputer which can simulate 2 to 30 states. 30 states. That's what we mathematically calculate for that. So, some computer when you simulate it, I will simulate 32. Beyond 32, I think the number is so large that you cannot simulate those states. Okay, so inherently, email has it 5,000 states. 30. Now, IBM itself has much more. 100 and now Australia has 232 weeks. So what? Second. The photo was to understand how to write concept. Okay, but first algorithm that was theoretically proven to be have much better performance. It has an exponential speed. अगर क्लासिकल में हम space to identify errors or function is an instant properties. But here it is single query we are identifying. Okay, secondly we added on the classical simulator package of simulator. Second, because state to state yes. But in the second state, we use something called the transpiler. So compiler is something which converts your INR and storing and is classical. Transpiler is converting this code and converting it into quantum circuit. So actual quantum circuit implemented for actual business. This is what we just usually saw in the code. But ideally it is taking that, it is converting that into actual quantum algorithm circuits, getting implemented by the backend service. Okay, backend is a service provided by IBM, which and there is something like this backend function. Yes. In United States for Europe, they have it. We also can know that which site data center is. So this code went to that site. So let me know if everyone has been able to come up to this point. So, the whole purpose of this exercise was, again repeating, to pick up the first best algorithm that was devised theoretically 20 years back, which claimed exponential speed as compared to the existing known classical methods. And then we tried just executing it for an n-bit input stream. Whether it is 1, 2, 3, 4 bit input streams, right? And we now see that in a single query we are able to do that. And we also saw that we executed it on a real quantum computing hardware. And because quantum computing systems have 2-3 issues. One is like they are inherently probabilistic, so you can't just run a job once. You have to run it at least 1,000, 2,000, 2,000, some number, 1,000, 2,000, 3,000 times to come up with a better calculation. There are multiple results for this. Okay, so one is like even on classical computers, the results cannot be relied fully. I was watching a video day before yesterday where NASA had done a huge amount of research on there are certain cases where classical computers के अंदर जितने भी classical devices हैं उसमें there is something called as high energy cosmic rays from the outer space. Okay, so and some cosmic rays come to the sun, but most of them come to, or these are high energy particles. अगर गलती से भी कोई high energy particle हमारे this is called as soft errors in classical computing. It's called as soft errors. Okay, so there was one lady in Europe जिसको अचानक से कुछ तो 4,000 कुछ तो votes से वो जीत गई. But when they actually calculated, there was a voting machine and people used to come for the elections, and then some several years back, then if I am doing voting and then going back, so they had this data across multiple booths at multiple locations, and the data also went to the server. So in the server, that one lady actually won with several 4,000 plus votes. So ideally what happened is that when they verified the data using their physical backup for every booth, at that time they identified that the actual votes are hardly 300, 400. Then out of this lady has got 4,900 votes and she has they verified all systems. So that is considered to be a problem of soft error, where high energy particles from the outer space can actually do a bit flip operation on your random access memory. Although the probability was initially considered very low, but now today we know that it is not easy, it can happen in a high amount of probability. उसके बाद बहुत सारे systems है, especially when you go and travel in an aircraft, जितना ऊपर जाते हो space travel में आप ज़्यादा से ज़्यादा cosmic rays को expose होते हो. Cosmic rays are high energy particles, some photons, some molecules, which is huge amount of energy, and they possess the property to go inside the bit, classical bit, and do the flip operation. So because of flip operation on some 8 push to 16 bit string था, उसका 1 bit को उसने 0 का 1 कर दिया, तो 4096 was added into that number of votes, and that lady got that. Secondly, there was a plane that was flying several years back, जिसमें similar thing हुआ था, because these are all automated things. Okay, the plane is not a manual drive, जिसको बस manually ऐसे घुमा के ये लोग लेके जाते हैं. There is a lot of automated electronics avionics system. So in the plane's electronics, somehow the bit flip operation occurred, which told that system कि आपको कुछ तो कमांड जनरेट हुआ जिसकी वजह से 2-3 बार एंड सेवरल पैसेंजर्स एक्चुअली बिट उसको क्रैश लैंडिंग करना पड़ा, सेफ लैंडिंग किया उन्होंने बाद में, पर उसको लैंडिंग करना पड़ा. देन दिस बिकेम अ मेनस्ट्रीम प्रॉब्लम. नासा हैज बीन कंसल्टिंग लॉट ऑफ एरोस्पेस कंपनीज ऑन दिस कि because of such phenomena that we are not knowing earlier, it is quite likely that our classical systems may not be also reliable. So then they started keeping up backups and resiliency, multiple copies, and then if all the copies, or even if one is false, then they don't rely unless and until multiple copies are giving the same signal. So bit flip operations के लिए corrections implement किए जा रहे हैं classical systems में. Quantum systems are so sensitive कि वो already sensitive है इन सारी चीजों की. Okay, so कुछ भी थोड़ा बहुत interference होता है. That's why इतना billions of dollar पैसा invest करके वो quantum systems को stable maintain करते हैं. So that is the main challenge for keeping the quantum hardware stable, and then lot of high-energy cosmic radiations interfere with your classical quantum hardware and the computations related to that. So that is one challenge. Second challenge, the nature of your quantum hardware is inherently probabilistic, so you have to run multiple times. So even though we ran our job for 2048 times or whatever, but still it gave me, algorithmically it gave me a speed up, but I am running the same job 2000 times more. Correct? So ideally, फिर मैं उतने input combinations set to raise to 4 में pass out कर देगा तो classical, that's why it is not quantum supremacy case. Okay, इसका disadvantage. क्योंकि इतना सब कुछ करके whatever effort we are doing, is it still worth it? We don't have that much, so this is what we are talking about. This term. Is it worth it? You still have to execute the parameter, even if I devise a quantum advantage. Is it still worth it? Because I have to run it multiple times to come to a deterministic conclusion to yes, this is what is my conclusion. So these are the combination of constraints that we need to deal with in order to make quantum software applications or quantum algorithms useful for the mainstream business or research. So we are advancing step by step. The best thing is that we have executed an algorithm now. Here we know, but unless and until we are doing it for a huge bit stream, okay, there is no point in doing that. Now consider that there is similar type of application where I have, let's say, some delay system, 5000 qubits, so it is a big number. On IBM Pixel, for example, it is 127 qubit system we have, 150 qubits. The number of qubits, if you increase in a quantum computing hardware, the amount of noise that is present actually increases, and that's why you have to run these many times to identify that we are assuming that most of the times there must be some signal to noise ratio, so that's why we are running it multiple times. So even after running it multiple times, and again we are unable to run it on larger data sets, so how can it be run on larger data sets, etc. etc. So understanding about the noise that is inherent in our computations in quantum computer. Eventually there is a lot of research going on. We have claiming that we have reduced the noise level, etc. But when we will be getting comparatively much lower noise for larger qubit systems, then definitely some of the algorithms already exist today which can claim a very great advantage as opposed to classical algorithmic problems. So now we will try to see if we have machine learning use case. But before that, I would like to show you some other algorithms. So this is a very famous algorithm, Grover's algorithm. This is a graph search algorithm. So we had some hands-on. I think now what I will try to cover is I will try to cover the breadth and to give you some views of the remaining algorithm. Just state you can try yourself is the non-machine learning, but basically robots, short conversion, or integer factorization, but the Fourier transform. Okay, these things we will go through. And then we will try to touch in the second half some topics like quantum machine learning, quantum cryptography, and where we will end this. So under CH applications, if you go, these are now it is available with the data. So remove it from there. So there are some examples that we will try to cover. For example, this is facial expression recognition application. It falls under quantum machine learning. Okay. So where facial expression, whether somebody is smiling or somebody is upset, that we can do. Okay. And I think because the input data sets are not too many, we can detect whether somebody is smiling or not. They have the data set as well. So accordingly, we can do that. Okay, so for example, this is a lady, she is smiling. If somebody who is not smiling, so you can identify. This is typical machine learning problem implemented in quantum. This is a beautiful case for quantum machine learning. Okay. Then again we have image processing for that. Some image processing. And then we have machine learning. So just implementing a basic hybrid quantum classical neural network for identities. This is also we will cover in quantum machine learning. So this is the architecture. Then we have classical layer, quantum layer, and then again we have PyTorch optimization. But how we can implement type of machine learning problems is unsolvable even using high-speed GPU clusters. Can I get a small subset of that problem and try to find out that it can be easily solved using quantum, and then try to either hybrid. If you couple your existing neural network architecture by embedding quantum layer, it is again quantum classical neural network. If we try to use some of the quantum concepts and use in the CC domain, it is called quantum inspired machine learning. Okay, and then there are various different types of algorithms and neural network types that are there. If we go to quantum neural network or quantum deep learning, then it has its own challenges, because the way we saw for executive mid-tier, a basic algorithm, okay, it has its own so many aspects. In a similar fashion, for quantum machine learning, it has its own problems. For example, of quantum convolutional neural networks, there are multiple years, multiple papers were published. So one paper said that there is a parent plateau problem. Okay, parent plateau problem. It was impossible to get better result in quantum convolutional neural network. So then somebody published that there is a method by which we can overcome that. So there are 2-3 series of papers around the same problem in quantum convolutional neural network. So today we know that there are methods which actually solve that problem, and then it does not stuck into local maximum local minimum or gradient descent point of view. So that is something which we have to study. Then there are multiple ways and means. So to start with, we will start with the quantum support vector machine, which are called quantum kernel methods. Okay, so support vector machine uses kernel methods. Kernels are functions in higher dimensional feature space, okay, which solve your classical comprehension by converting your data into higher dimensional feature space, and then you again have transformation, solve it in a higher dimensional feature space, and reverse transformation to a lower dimensional feature space. That is how support vector machines actually work. Okay, IBM itself published a paper in quantum support vector machines using quantum kernel methods, which I will try to walk you through that. So the June 2021 conference of IBM, there were multiple researchers from the world. Okay, people trying. This is still on IBM website. So researchers from the world actually did handwritten notes, and these are part of the documentation of IBM. There were very few people, even 3 years back, 2 years back. So this has become their lecture series, which has eventually converted into IBM documentation. ये जो हम जब सब बात किया ब्लॉकस्फीयर वगैरह, this is all part of the IBM notes, some well states. So 2.1 lecture I will show you. You see, whatever we talked about quantum circuits, same thing was discussed in June 2021 IBM Summer Symposium. Entanglement, teleportation, etc. Quantum algorithms. So the same algorithm that we have discussed, this was presented in June 2021 Summer Symposium. Okay. So we are given a function realized by an oracle of which we know that it is either a constant function or a balanced function. All inputs map to the same output, and number of inputs mapped to 0 and 1 are equal. This is a balanced function. So this is the this is Grover's algorithm. These were the nodes. Now today we have these nodes also converted into then other quantum algorithms. This is again Gauss's algorithm. This is the circuit. How will you implement the circuit? Then Grover's algorithm. Classical machine. We will move to this point. Quantum machine. But before going here, I would like to just quickly summarize some of the algorithms here. We will not run them right now, in the interest of time. But similar to Gauss-Joseph algorithm, let's try to go to this algorithm. So, the answer to your question, Bernstein Basset, this algorithm is the extension to Gauss-Joseph algorithm. So, here is its classical solution and quantum algorithm. See, it can be seen as an extension to Gauss-Joseph algorithm. We covered in the last section. It showed that there can be advantages using quantum computer as a computational tool for more complex problems. And so here we are given a black box function which returns either 0 or 1. That is this. Instead of the function being balanced or constant, as we found out in this algorithm, now the function is guaranteed to return the bitwise product of the input string, input with some string. In other words, given an input string, input x and fx is equal to s dot x mod 2, we are expected to find s as a classical reversible circuit. So basically it is finding out the whole. So what was the input string is what it is trying to find. This is that algorithm. Again, I will not go into in depth because we will not be able to cover other topics on this. And this is the second algorithm we should go through. Third is Simon's algorithm. From Simon's algorithm, you will see that it is more relevant to our practical problems of interest. This is an algorithm where so the first algorithm to show an exponential speed up versus the best classical algorithm in solving a specific problem. So in classical domain, whether to find the function is balanced or not is not a big problem, but this is something where this inspired the quantum algorithm based on the quantum Fourier transform, which is used in most famous quantum algorithm, Shor's factoring algorithm. So this is a so Simon's problem. What it figures out is basically we are given an unknown black box function which is guaranteed to be either 1 to 1 or 2 to 1, where 1 on 1 or 2 to 1 functions have the following properties. So the 1 to 1 maps exactly one unique output for every input. An example with a function that takes 4 inputs is that if for 1, 2, 3 and 4 input values it will give me some output, get exactly one input. So this is a 1 on 1 function. Okay, so and this is a 2 on that function that is which maps exactly 2 inputs to every unique output. So this is a 2 to 1 mapping. So given this black box function, how quickly can we determine whether a function is 1 on 1, 1 to 1 mapping or 2 to 1 mapping? If function turns out to be 2 to 1, how quickly we can determine the P? So this is Simon's algorithm. Again, there is a circuit related to that. So now the steps to follow is that after these 3 algorithms, I think the sequence should be to understand quantum Fourier transform first. So this is a very useful tool. So quantum Fourier transform has been a building block for quantum phase estimation algorithm, and then that is used for reverse search algorithm, which is a graph search algorithm. Then it is also basis for Shor's algorithm, which is the integer factorization algorithm. And from Shor's algorithm to reverse algorithm, we enter into a domain where there exist algorithms which can beat the existing classical methods, provided we have larger qubit systems. But it goes on a bit complicated. For example, quantum Fourier transform, we have to understand this first, different phases, and then how quantum Fourier transform is implemented as a quantum circuit. For an n qubit input stream, how to implement the quantum Fourier transform method in the black box. Then that we will use within our Shor's algorithm. This whole tutorial is about implementation of quantum Fourier transform. And then, if you go and see Shor's algorithm, inside Short's algorithm, see, inside Short's algorithm, we use quantum Fourier transform as a module here. Okay. So, how should we go? There are these three algorithms: quantum Fourier transform and Shor's algorithm. Basically, so these are two-phase quantum phase estimation. We have quantum Fourier transform and Shor's algorithm, which we can quickly go through. And then the next thing remains is two examples of quantum machine learning, which we can work out on the after this lecture. And I have some slides that talk about quantum machine learning. So, thanks a lot. I think if you have any questions, let me know what I will do. I will pause for now. I have shared some of the data on the same GitHub page. Right? So what we can do is two algorithms and it's go to one is Shor's quantum Fourier transform and Shor's algorithm. You can just go through it, we will try to execute. Then we have quantum machine learning, two examples we will try to cover. And then the theory related to quantum machine learning after 2 p.m. we will cover all these things. Yeah.
Thank you, sir. Thank you for this hands-on session. You really showed us the glimpse of real-world implementation of quantum algorithms and how we can go ahead for our research in this direction. That also you have very much enlightened us with. Your case studies regarding the facial recognition, edge detection. I am sure that many of us will have lot of doubts, isn't it? Right? And maybe we would like to cover it, or we would like to explore those doubts and get it cleared from you in the second half session. So thank you so much once again. I hope all the participants have enjoyed this session. If at all you have any doubts, sir is available. And yes, please make the most of it in the second half, because sir is there with us only for today. So what all doubts you have, better you list it out and you can surely ask us, right? Thank you so much. Thank you, participants. Please.
Good afternoon, participants. We have few announcements, and then we have the session of teaching practice and article discussion. First announcement is regarding industrial visit. As per schedule, we have industrial visit on Thursday, 7th of December, and we are going to Pune, and we are visiting two facilities. First one is ICER Pune campus. There is Quantum Computing Hub, iHub, established by Department of Science and Technology. Hundreds of crores are invested in that hub, and there are very nice equipments available in the domain of quantum computing. Hardware also, we will get a chance to visit that facility. So we have 2 hours visit there. Project director first of all will give us 30-minute overview kind of thing about iHub, what are the facilities they have there, and according to the groups we'll have to move to the iHub facility. There will be the technical assistant with us. We all together cannot move into their labs because they are quite, size is not that much big. So five members we will go inside and we will visit the facility and we will come out. So we have 2 hours visit over there. Institute have already arranged a bus with a capacity of 49 seats. So don't worry about that. You just have to reach to college gate, Vidya gate. The reporting time is 7:30 and sharp we will be starting at 8 a.m. to Pune. So I request everyone to cooperate, because even if a single member is not able to reach and if we are not able to start at 8, the things will get delayed and project director will not be available if we don't start our visit at 11 o'clock. So we all will assure that we start our journey 8 a.m. in the morning. Institute have already arranged the breakfast. We are having the packets of breakfast, sandwich, muffin, some biscuit packets. So please don't carry any kind of food with you. Water bottles also we are carrying. Additional you can keep with you. So breakfast, once we start journey, we are on the expressway, we can have the breakfast in a bus only. Then 5-10 minutes break we will have. After crossing the toll, we can get fresh, and in 10 minutes we will start the journey. Lunch arrangement is done at ICER only. We have already taken the coupons for the lunch. So 1:30 we will be proceeding there in the ICER canteen for the lunch. So that all arrangement is done. We have to assure that we start to Ayuka at 2:15 from ICER, because their people are very much particular about their time schedule. So we have to cooperate them. So once we are done with ICER Pune, iHub visit, lunch is done in the ICER only. We will move by bus to Ayuka Pune. It is a center, inter-university center for astronomy and astrophysics. They also wanted to show us something through telescope. They have their project, but because of time constraint, we could not do that. But we wish in future, if you get opportunity to visit Ayuka, please see that. It's a beautiful facility at Ayuka. So once we enter Ayuka, we have 1.5 or visit at IOCA. Their PQM measurement lab is there. So precision and control measurement lab will visit again in small groups, 5 members. And once that visit is done, we'll start our return journey. So we're planning to start at 4 at least from Pune, so that we can reach well in time in Mumbai, considering the traffic conditions. Important point, I have people, the projector director conveyed, the equipments are very costly. So a single touch should not cause any damage. So we will take care, okay, we will not touch any of the equipment present over there. That is our personal responsibility. Even myself or anybody else among ourselves will take care कि गलती से भी थोड़ा धक्का लग गया है तो ऐसा हम कोशिश करेंगे कि हमसे ऐसा कुछ ना हो. Because the way they instructed me, they took 1 hour to convey all the instructions. I am summarizing in short time. So we know we all are responsible, but due care we all will be taking. And it's a golden opportunity to visit that facility. So take as much as possible through that visit. The equipment, you never know how you can get associated in future with IHUB ICER as well as IOCA. They have already floated a brochure. ICER Pune have hundreds of crores grant in hand to give it to the individuals, but that is a startup grant they have. I asked them, is there a scope for research proposal? They said no. If anybody is interested to register a startup in quantum computing, please let us know. So I will share that document in a group immediately. So if you have a plan, if somebody is working in the quantum computing, or your associates may be at your workplace, please circulate them and you can fetch DST grant through that proposal. So many opportunities are coming to us. It may be a single start for that, and you never know, next year you might be having some grant with you or some startup thing kind of thing. So this was about industrial visit. Second thing is quick update on the participants who are traveling like beyond 20 kilometers. You need to contact Jyoti Joshi madam in the IT department and give your travel tickets to her. She will tell you what all documents are required along with the account details. Hope regarding TA there is no question. Tickets you have to submit hard copy to Jyoti madam and she will share a drive link. Then you have to upload soft copy also. So I suggest you scan it